Ladies and gentlemen, it's the day you've all been waiting for. It's the perpendicular bisector theorem. That's it's Miss Teeter in the hizzy here. We're going to leave that in because that's just fun. All right. Perpendicular bisector theorem. I've been talking about this one for the past few days, probably the past few weeks, because I just love it. It's kind of confusing. It's a little weird, but it's all powerful. Okay? It's like the most powerful of theorems in this class. Alrighty, so the perpendicular bisector of a segment is a line that both bisects the segment and is perpendicular to the segment, right? Like that makes sense. That's the definition, okay? So if you know something's the perpendicular bisector, like if I told you it was a perpendicular bisector, let's say we've got what it says here, E and G, that segment, and it's the perpendicular bisector to DF, so D, and that'll be F. That means that it's perpendicular to, so I get right angles from that. I can put that in the proof. I can say, oh, we got right angles. Right angles are congruent. Yay! And it's also bisecting, which means it splits it into two congruent pieces. Okay? That's what it is. All right, but it's our theorems involving the perpendicular bisector that help out even more. All right, so I've redrawn what we had on the last slide. Actually, I think I switched the G and the E letter, but that's all right. No big deal. It says if a point is on the perpendicular bisector of a segment, then it is equidistant to the endpoints of that segment. So in the last slide, we drew EG to be perpendicularly bisecting DF. So I knew that these two are congruent. We have our right angle, right? And what it's saying is that any point that is, any point that is on this line, EG, is equidistant to D and F. Okay? So if I have a point here, this point is equidistant to D and F. Boom. If I got a point here, it's equidistant to D and F. So basically what we end up getting here is we get a bunch of pairs of congruent segments if we want them. So these two would be congruent. If I know that EG perpendicularly bisects DF, I can prove those two red ones congruent. I can prove that ED and EF are congruent. So I can prove that those two are congruent. Pretend I drew those line segments nicely. Okay, I can prove that DG and FG are congruent. I'll make a circle on there. Yay! Cool. So I can prove all sorts of congruent segments if I've got a perpendicular bisector. All right? Cool. And we can abbreviate this as PBT. So if I have a perpendicular bisector, I could get a bunch of pairs of congruent segments. But what if I don't have a perpendicular bisector? Is there a way to prove that something's the perpendicular bisector so I can get a bunch of other segments pairs congruent? I'm glad that you asked. So we also have the converse of the perpendicular bisector theorem. Now we're not actually going to prove this one. I just want to get into using it, but let's talk about it here real quick. So say we've got our lovely situation that we had from before. All right, we got, I don't remember what they were, but I think it was like D and G. Maybe it was D and F. And then we had E and G, let's say. Okay. So what this theorem states here is if 2 points are each equidistant from the endpoints of a segment, then the 2 points determine the perpendicular bisector of the segment. So let's say I didn't know that EG and DF, or EG perpendicularly bisects DF. But let's say I had this line here, and I'll say that these were congruent, and let's say that I had these two were congruent. I can then prove from the perpendicular bisector converse that EG perpendicularly bisects DF. And once I have that, I can then prove maybe these two segments are congruent if that point is on EG, the line segment that perpendicularly bisects the other. Or maybe I wanted to prove these two segments congruent. Or maybe I wanted to prove these two. You know, any number of them I can now prove congruent to each other from the perpendicular bisector theorem. But in order to get that, I used the converse to prove that it was a perpendicular bisector. Oh my goodness, this is so confusing. Let's try it in a proof and see how it's actually used. Alrighty, so we've got AB is congruent to BC, and we've got AE is congruent to EC. Let's mark those. I want to prove that AD is congruent to DC. Now in the past, I could have gone through a whole detour proof, proving some triangles congruent to get more information about other triangles, to prove those triangles congruent, and it would just be wonderful, right? You know, I'd probably end up proving the ABE congruent to CBE, and then getting some angles, maybe a little subset congruent. Oh geez, it'd be awful. But with this new theorem, let's see here. If I look at line segment BD, and I'm just going to draw a line right through it. If I look at that line right there, you notice how E is equidistant to both A and C, because those two segments are congruent, and B is equidistant to both A and C. So by my perpendicular bisector theorem converse, I would know that BD perpendicularly bisects AC. I'm going to jot that down. So I've got my given, and here I can say that BE, line BE, which would include BD and our point F there, right? I could name it anything. I'm just naming it BE because those are the 2 points that are equidistant. Perpendicularly bisects segment AC. And that'd be by the perpendicular bisector theorem converse. Okay? So in order to prove that it's a perpendicular bisector, I can use the converse to do that. Now that I have that it's a perpendicular bisector, well, D is a point that's on the line BE, right? Heck yeah, it is. So I could say that AD is congruent to CD. AD is congruent to CD, or DC, I guess, in this proof. I can say that those two are congruent by the perpendicular bisector theorem. That is the original, the OG of perpendicular bisectors. 3 steps, no detour, nothing, taking care of it. Heck yeah. Alrighty, so the theorem is really our most powerful. The definition just tells us what it is. It does give us a perpendicular, and it does give us a bisecting that's happening, but the perpendicular bisector theorems are the ones that help us get all these other congruent segments. All right, I think I remember from, 4.1, when we first introduced detours, we saw a problem like this. So it was similar to this. It might have been rotated slightly different. But in any event, we had angle B congruent. That is in a bad spot. Let's see here. There we go. It's a little better. And C were congruent to each other, and I have circle O. And we did this one in about 10, 12 steps. It was obnoxious, yeah? Well, I just want to prove that AO is perpendicular to BC. So the great thing about the perpendicular bisector theorem is that if I prove that it's a perpendicular bisector, it's already proved that it's perpendicular, right? And then you also got bisecting along the way, but it gets the job done with a little bit of extra. So let's see if we can do this in 5 steps without proving triangles congruent. Alright. Now I know if I want to get a perpendicular bisector, I need to get 2 pairs of segments congruent. And I want AO to be the one that's perpendicularly bisecting BC. That's what it seems like I want here. Well, if I get AC congruent to AB by if angles and sides, I've already got 1 pair. We did that in this proof before. Well, I probably could draw in some radii, which I know are congruent to each other. All radii are congruent. Oh my goodness, look at that. We've got AO is a perpendicular bisector of CB. It's perpendicular. Lovely. I'm already ready to write this proof up. Let's do it and make sure we make sense of all this stuff. So I've got AC after my given. No, Siri. I don't need any help. I don't know why that goes off randomly, but it scares me. All right, AC is congruent to AB if angles, then sides. Lovely. It's a triangle. I can do that. Remember, that only works with triangles. That's why we draw the triangles. We know what triangles are. Now I'm going to draw, what was it, CO and BO. Let's see here. That's aux line, or 2 points to determine a line. Whatever works for me. Alrighty. I got CO and BO are congruent, right? So BO is congruent to CO, all radii congruent. Now, since I have CO congruent to BO, I've got AC congruent to AB. That shows that A is equidistant to both B and C. O is equidistant to both B and C. So those 2 points determine the perpendicular bisector. That means that AO perpendicularly bisects BC. Since the proof is only perpendicular, I'm cool with you writing perpendicular to BC, or we can say perpendicularly bisects. I'm going to put that in parentheses. BC. I'm going to extend my, there we go. I'm going to put that in parentheses just because it's really not part of the proof, but it is there. It is happening. We can jot that down. I'm not going to be too picky on that. And my reason for this one, well, I've proved that it is a perpendicular bisector. That is the perpendicular bisector theorem converse. I'll pop a little C over there for the converse. All right, PBT, C. YOLO. Swag. All right, this theorem is quite confusing. If you do have trouble with it, make sure you ask some questions on it. We'll do some more practice with this. Practice for our quiz, which is coming up. Woo-woo. Alrighty, so on our homework tonight, or whenever you're doing this, it might be midday, it might be right before class, who knows. Do it without proving congruent triangles, okay? Those are the number of steps you should have for each one of your proofs. You should be using your perpendicular bisector theorem or the converse or both in these proofs. Alright? No congruent triangles. Work on the perpendicular bisector theorem. P, B, T, or P, B, T, C. YOLO.